All right, everyone, this is where things get really fun when looking for general solutions to homogeneous differential equations of the second order. What happens if our characteristic equation gives us a complex solution or complex solutions? So let's take a look here at this example. We're going to find the general solution to y double prime minus 4y prime plus 5y equals 0. So we'll start as we always do. We're going to start with the characteristic equation, r squared. Let's do this in black here. R squared minus 4r plus 5 equals 0. And we could sit here and try and factor this all day long, and it's not going to work without complex numbers. So we'll use the quadratic formula. So r is going to equal positive 4 plus or minus the square root of 16 minus 4 times 1 times 5. There'll be a 20 there. And then this will be all over 2. So we'll go ahead and simplify this down here. We're going to have 4 plus or minus. This is going to be the square root. 16 minus 20 is negative 4. So we'll have the square root of negative 4 is 2i all over 2. And when we break this into two fractions and reduce, we'll get 2 plus or minus I. Okay, for this problem, for our introduction here, we're going to do a couple of things. We're going to say, what's the general form for a solution when this occurs, when we have complex solutions to the characteristic equation? And then we're going to do that, use it for this specific problem, and we're going to show that it works for this specific problem. And then I'm going to make a separate video showing where that general solution that I'm about to show you comes from and prove that it works in a separate video so that we don't have this one be too cluttered here. So generally speaking, if we get r equals a plus or minus bi from our characteristic equation, hey kitty. My cat wants attention. He's going to have to wait. Then the general solution is going to be y sub g of t. Come on in. Move this down just a hair. Is going to equal e to the at parentheses d1 cosine of bt plus d2 sine of bt. So what happens when we have complex solutions here is that complex solutions to the characteristic equation means that our function y of t, the general solution to the differential equation, y sub g of t, is going to be an exponential times a cosine and a sine function. So we get more of wave-looking solutions instead of just exponential solutions when this happens. This is going to be really interesting as we start looking at harmonic oscillators. If you take a mass and put it on a string and pull it back and let go, we can model how that mass is going to move. That's a basic example of a harmonic oscillator. We get into things like pendulums, and that's a harmonic oscillator swinging back and forth. We have planets circling a sun is a harmonic oscillator, and we can model that using second-order differential equations, and so on and so forth. So obviously right now we're doing the pure abstract theory behind this, and then we'll get into some applications later on this term. All right, so let's take this and note for here we have a equals 2 and b equals 1. So for us, the general solution, y sub g of t, is going to equal e to the 2t parentheses d1 cosine of 1t, right? So that's the b value right there. The a value goes into the exponential, plus d2 sine of 1t. And obviously we don't need to write those ones. I'm just trying to be clear about where I got that number, what goes right there next to the t inside the cosine and the sine. I was going to say hi to my kitty. This is Loki. All right, Loki. He's got a brother named Thor that's running around here somewhere. Okay, let's keep going. Sorry. So we want to check now and see that this actually works for this specific differential equation so that I'm not just fooling you. So to do this, I need the first and second derivatives. These are going to get a little messy here, so I'm going to zoom in, write a bit smaller. My first derivative for this is the derivative of the first is 2e to the 2t times the second, d1 cosine of t plus d2 sine of t. And then we're going to go plus the first, e to the 2t, times the derivative of the second. So inside we're going to have negative d1 sine of t, and then plus d2 cosine of t. And now we're going to recombine this. I'm going to factor out the e to the 2t, and I'm going to combine my cosine terms. So here I've got a 2 d1 cosine and then a d2 cosine over here. So those are going to add up to 2d1 plus d2 cosine of t. And then we're going to add together the sine terms. So I have a 2 and then d2 sine of t and then a minus d1 sine of t. So that's going to add up to 2d2 minus d1 sine of t. Close this with a black line here. Cool. So that's going to make it a little bit easier to take the derivative again. So y double prime sub g of t equals the derivative of the first is 2e to the 2t times inside the derivative of cosine is negative sine, so I'll have a negative 2d1. Oh, I'm sorry, I don't need to take the derivative of the inside yet. We're just going to copy the inside down. 2d1 plus d2 cosine of t plus 2d2 minus d1 sine of t. And now we're going to do plus the first, e to the 2t, times the derivative of the second. So now is where I'm going to go ahead and take the derivative of that inside. So I'll have a negative 2d1 plus d2 sine of t here. And then plus 2d2 minus d1 cosine of t. And we again want to combine our sine and cosine terms. So I'll factor out the e to the 2t from everything. And then cosines, we have a 2 in front, and then a 2d1 plus d2. And then over here on the right, we have a 2d2 minus d1. So my d1s are going to be 4d1 minus d1 is 3d1. And then plus, I have 2d2s, and then another 2d2s is 4d2s in all, cosine of t. And then plus, now we'll look at the sine terms. We have a 2 in front of this first one here, and then we've got the 2d2 minus d1, and then over here we've got a minus 2d1 minus d2. And so when we put that all together, let's do d1s first. I've got minus 2d1 over here, and then minus another 2d1 is minus 4d1. And then the d2s, I've got 4d2s in the first here, and then minus d2 is minus, or is plus 3d2 rather. I've got 4 minus 1 d2 equals 3d2, and that's our sine factor. So we now combine those. I hope that was okay to follow along with there. All right, we now want to check. We now want to plug these into the original differential equation. So I'm going to show it nice little way of organizing our work here. What I'm going to do is I'm going to take all three of these and I'm going to multiply them using parentheses here. So y sub g needs to be multiplied by 5, and then y prime of g needs to be multiplied by a -4, and then our y double prime is going to just be multiplied by a 1, right? So I'm just looking at the coefficients of y double prime minus 4y prime plus 5y, so that I can go ahead and multiply those across here, and then we can combine the like terms. So on the left, we get 5y minus 4y prime plus y double prime, and then equals, all right, so we're going to have e to the 2t in front of all of them. I'm going to open up parentheses, and then I'll do my cosines in red again. So let's look at our cosines. We've got 5d1 up top. I'm going to do this 5d1 plus, or in the second one I've got minus 8d1, and then in the y double prime one I've got plus 3d1, and then the d2's at the top we don't have any for cosine, and then in y prime I've got minus 4d2, so minus 4d2, and then in the last one it looks like we have a plus 4d2. That's good. That's what we're looking for. We want all of this to cancel out, and we can see that those are all going to add to 0 here. And my signs in purple. So from the original function we have 5d2, and I think I'll distribute this a little bit differently this time around. In the second one I'm going to have negative 8d2 plus 4d1, and then from y double prime we will have minus 4d1 plus 3d2. Might be a little bit easier to follow along there. Organizing it that way. This is in green. Roll. And so the left side gives us 0 because, I want to say sub g's on these. It's y sub g, y prime sub g, y double prime sub g. And those we know add up to 0. I'm sorry, I said that wrong. That's what we're trying to show adds up to 0 to state that y sub g is a solution. So we do have 5 y sub g, or I'll put it in the original order so that we can see it exactly in that way. This is y double prime sub g minus 4y prime sub g plus 5y sub g. Equals, on the right side we have e to the 2t times 0 times cosine of t, right? The d1s all add to 0, the d2s add to 0, plus then the sines 5d2 minus 8d2 minus, or plus 3d2 is 0, and then 4d1 minus 4d1 is 0 sine of t. And so this equals 0. Therefore, the y sub g that we found, e to the 2t times d1 cosine of t plus d2 sine of t is, in fact, a solution to y double prime minus 4y prime plus 5y equals 0. End proof. All right. So, most of the time we're not going to be checking these. There might be one problem or something in your homework where you need to check something like this, just to, kind of go back through these motions, see that it really does work. But in practice, we're really able to just use this formula up top, and we're just getting that general solution, and then we'll use the general solution which will to find a particular solution given initial conditions, which is what we're going to do in the next video. And then in the last video for today's lesson, we'll go through the proof of where that general solution that we get for these complex roots to the characteristic equation comes from. All right, thank you much, everyone, and we'll see you in the next one.